The production of blood cells, and by blood cells I mean all of them, the production of blood cells or formed elements is a process called hematopoiesis. This process takes place in the bone marrow and begins with what is called a pluripotent hemopoietic stem cell, or alternatively a multipotent hemopoietic stem cell, shown here. Now, a stem cell is a cell that has the potential to develop into a number of different cells. An embryonic stem cell has the potential to develop into almost any tissue in the human body, whereas a hemopoietic stem cell can only divide and produce any type of blood cell or formed element. The process of taking a stem cell and ultimately producing the final product here is called differentiation, or hemopoiesis, but it goes through a process called differentiation. And what this means is, thanks to chemical signals that this stem cell is exposed to, the stem cell will begin to specialize. And it might specialize into one of two different pathways. The first pathway, the myeloid pathway, the multipotent hemopoietic stem cell begins to specialize, differentiate, and in this myeloid pathway, it will further divide to produce our red blood cells ultimately, and our platelets, and our myeloblast white blood cells. These would be your neutrophils, eosinophils, basophils, mast cells, and other, did I skip anything? Monocytes. That's what I missed. On the other hand, the stem cells might go through the lymphoid stem cells, become a lymphoblast, and ultimately become a lymphocyte. As I mentioned, this whole process occurs in the red bone marrow. Now, we do have such a thing as yellow bone marrow. Now, yellow bone marrow can actually be held in reserve in case we need it later. Yellow can become red bone marrow. So if you were to experience a major loss of blood, for example, you would be able to regenerate that blood faster because the yellow bone marrow can temporarily transition to red, and then it will transition back to yellow when it's no longer needed. Here's that differentiation process that I talked about, or actually the vocabulary word there, where we begin to develop in response to chemical signals. Okay, and we're going to talk a little bit about those chemical signals. Now, specific to hemopoiesis is the broad umbrella term. A much more specific term for the production of red blood cells is called erythropoiesis. This process involves differentiating from the stem cell into, at each stage, a pro-erythroblast, an erythroblast, a normal blast. We get rid of the nucleus and we become a reticulocyte. There's a few ribosomes hanging on in the reticular site. And then, generally speaking, this is where it exits the bone marrow into the blood. Once in a while, a reticulocyte will escape into the blood before it's become a complete erythrocyte. And so you usually do have a low number of the reticulocytes, but they're not common. This process of development, beginning from the pluripotent or the multipotent stem cell, involves a chemical messenger known as erythropoietin. When the stem cell is exposed to erythropoietin, so this blood cell here, that's when it begins to commit or differentiate to this pathway. Exposure to erythropoietin is necessary for about the first 21 days, give or take. after those 21 days, okay, first 13 to 14 days. After those 14 days, we reach a point where we need to incorporate the iron, and that's the iron dependency stage. All total, that's going to take 21 days. That's where that comes in. And then about 2 days later, we are ejecting the red blood cells. So you might, if you've donated blood, you know that they require you to wait a certain period of time before you can donate it again. And the reason is to give time for this process here to replace your red blood cells. Now, the process of erythropoiesis is governed by erythropoietin, abbreviated EPO for short, and that in turn is governed by the kidneys that respond to low blood oxygen levels. We're going to take a little bit of a closer look at that. So here you can see the chemical pathway, or the cycle, if you will, for erythropoiesis and the release of erythropoietin. I want you to understand and know this, and we'll think about it and talk about some different processes that are some different factors that affect this process. The entire process of erythropoiesis is stimulated when the kidneys detect a low level of oxygen in the blood. Now, this low level of oxygen can be for a number of reasons. It could simply be because we've moved from California to Colorado, and there is a significant difference in altitude, and therefore we are, at least for the first few weeks, struggling a little bit to get sufficient oxygen into our bloodstream. Or perhaps my oxygen levels are low because I'm a chronic smoker, and smoking tends to damage the lungs, and as I've smoked for years and years and years, eventually the ability of the lungs to exchange oxygen with the blood is significantly affected, negatively so, and so as a consequence my blood oxygen levels have dropped. Or maybe I'm an endurance athlete and I do a lot of aerobic exercises, and so because I push my body repeatedly and I accumulate this oxygen debt. You'll remember that if you're working at about 50 to 70%, you're already beginning to build up that lactic acid, 60 to 70% of lung capacity. So maybe that's what's happening as I exercise all the time, and so my blood oxygen levels sometimes are low. All of these things will stimulate my kidneys to start producing erythropoietin. This is a cytokine, technically speaking, although some call it a hormone. It's classified as a cytokine because it affects a blood cell. But for all intents and purposes, it works like a hormone. It's released into the blood. It travels through the blood until it reaches the bone marrow. In the bone marrow, it encounters those stem cells. Remember those pluripotent hemopoietic stem cells? They have receptors on their surface for erythropoietin. So the erythropoietin will bind to those receptors like so, and that's going to stimulate the stem cell and cause the stem cell to begin to divide and become the precursor cells that are needed for red blood cells. Over the course of that 21 to 23-4 days, that stem cell will develop until it becomes a reticulocyte, which then becomes an erythrocyte. And then as the levels of erythrocytes build up in the bloodstream, each of these little sacs of hemoglobin will carry oxygen, and so the ability to capture that oxygen in the lungs goes up, and as a consequence, the red blood cells bring my oxygen blood level back to normal. Well, normal oxygen blood level is going to inhibit the release of that erythropoietin. So we have a situation where here we've got our negative feedback. This is the initial stimulus. This would be, therefore, an integrating center because it reads that stimulus. It generates an output, which would be my erythropoietin. And that erythropoietin travels to the bone marrow, where my stem cells become a second integrating center. Erythropoietin is now the stimulus for this one. It generates an effect, and that effect is to become red blood cells. The red blood cells carry the oxygen, and we return to normal. And so this cycle occurs as necessary. Maybe our red blood cells simply have gotten old and it's time to replace them. There are so many reasons why blood oxygen levels might go down. And so this process is critical. Now, one quick note about the erythropoietin. EPO has gained some notoriety because it is one of the common ways that we have, or that common chemicals that is used for blood doping. So people who want to blood dope, for example, Lance Armstrong was accused of blood doping with erythropoietin. They inject themselves with this synthetic cytokine, and then that cytokine stimulates this process of erythropoiesis. More red blood cells mean more oxygen carrying capacity. If you're an endurance athlete, this is very critical. You will tire less quickly. Red blood cells do in fact get old. Okay? They only live that 120 days, give or take. And when they get old, what happens is they become very fragile. Remember, these are not replacing their proteins. They're these fragile sacs of hemoglobin now. And as they travel through places like the spleen, with all of its branches and tiny capillaries, these old blood vessels tend to break. They are gobbled up, the old ones gobbled up by macrophages, and those macrophages destroy the cells and recycles the iron, binding it to transferrin, and then this ring here, this ring structure here, becomes our bilirubin. Now that bilirubin, okay, is then sent to the liver, and in the liver it can be conjugated and will then be eliminated from the body by releasing it into the bile, and it will then be excreted in the feces, or some amounts of it, not much, but some of it will actually be converted into something called urobilirubin, which is excreted from the kidneys. Sometimes bilirubin is elevated, which leads to a condition called jaundice.